Before we begin, we're going to review some terminology. Here's the definition of a reduced residue system. Definition: the set of integers r1, r2 up to rs is called a reduced residue system modulo M if the GCD of Ri and M is 1 for each I, if Ri is not congruent to Rj modulo M whenever I is not equal to j, and for each integer n that's relatively prime to M, there corresponds an Ri such that n is congruent to Ri mod M. We noted in the video for that section that the notation ZSubM Star is often used to denote the reduced residue system built from the set Zm by removing the elements that are not relatively prime to M. This notation is not used in the book but is very common in modern mathematics. Here are a few of those sets written out explicitly to remind you how they look. For each value of M, we can look at what happens when we take powers of the elements in ZSubM Star modulo M. Here are examples when M is equal to 5, 9, and 10. There are some patterns that we can immediately observe. The first is that for any a in Zm star, a to the phi of m is congruent to 1 modulo m. We actually already knew this, as it's just Euler's theorem from section 5.2. But you might also notice that some elements reach 1 sooner than that. This leads us to our first definition. Definition: if h is the smallest positive integer such that a to the h is congruent to 1 modulo m, we say that a belongs to the exponent h modulo m. The language in this definition is a little bit dated. Not many people use the phrase belongs to the exponent h these days. So we will use a more modern language and introduce a different definition. In fact, in several places in this section, we're going to reword things to frame them in a way that uses modern language. We will retain the numbering to allow for easy cross-referencing. Definition: if h is the smallest positive integer such that a to the h is congruent to 1 modulo m, we say that a has order h modulo m. For example, this would mean that the order of 1 modulo 9 is 1, the order of 8 modulo 9 is 2, the order of 4 and 7 modulo 9 is 3, and the order of 2 and 5 modulo 9 is 6. Theorem: a to the b is congruent to 1 modulo m for some integer b if and only if the GCD of a and m is equal to 1. Suppose a to the b is congruent to 1 modulo m, and let d equal the GCD of a and m. First, observe that there exists an integer k such that a to the b minus km is equal to 1. Next, observe that since d is the GCD of a and m, we have that d divides a and d divides m, so that d must divide a to the b minus km. Therefore, d divides 1, and so we must have that d is equal to 1. In other words, the GCD of a and m is 1. Now suppose that the GCD of a and m is 1. By Euler's theorem, a to the phi of m is congruent to 1 modulo m, and hence a to the b is congruent to 1 modulo m for some integer b. Theorem: if the order of a modulo m is h, and a to the s is congruent to 1 modulo m, then h must divide s. Suppose that a to the s is congruent to 1 modulo m. By the division algorithm, there exist integers q and r such that s is equal to hq plus r, where 0 is less than or equal to r less than h. Now notice that by substituting this in and simplifying, we find that a to the s is congruent to a to the r modulo m. By assumption, we know that a to the s is congruent to 1 modulo m, which implies that a to the r is congruent to 1 modulo m. But since h is the smallest exponent for which this happens, and r is less than h, we must have that r is equal to 0. In other words, h must divide s. Definition: if g is an integer, and the order of g modulo m is phi of m, we say that g is a primitive root modulo m. Looking back at the charts from earlier, we can see that 2 and 3 are primitive roots modulo 5, 2 and 5 are primitive roots modulo 9, and 3 and 7 are primitive roots modulo 10. If you look, you'll see that for each of these elements, the various powers of it cycle through the entire reduced residue system. That observation takes us to the next theorem. Theorem: if g is a primitive root modulo m, then g squared up to g to the phi of m are mutually incongruent and form a reduced residue system modulo m. Suppose r and s are chosen between 1 and phi of m, with s less than r, and that g to the r is congruent to g to the s modulo m. This implies that m divides g to the r minus g to the s. In other words, m divides g to the s times g to the r minus s minus 1. Since we know g and m are relatively prime by Theorem 7.1, we must have that m divides g to the r minus s minus 1. But this means that r minus s is a positive integer less than phi of m, such that g to the r minus s is congruent to 1 modulo m. This is impossible since the order of g is phi of m. Therefore, g to the r is not congruent to g to the s modulo m, and the listed elements are mutually incongruent. And since we have exactly the number we need, we must have a reduced residue system modulo m. If you've taken a course in abstract algebra, this section should seem familiar because all of these proofs are usually done in that course as well. An alternate name for the primitive root modulo m is a generator of the multiplicative group ZSubM Star. In class, we will look at a few more properties that we can derive regarding the orders of elements and primitive roots.
Thank you for watching this video. I'm currently dabbling with the idea of creating more videos like these for my classes, and I welcome constructive comments that might help me make better videos in the future.